All right, so like I said, we're continuing the 2D notes. We've on the front page already done the transformations and reflections. And then on the back side of that, we've done the stretches and compressions. And so now we're at the bottom of the back side that looks like this. So what we're going to be doing on these examples is we're going to use function notation to represent a function with the given transformations. So instead of being given the function that's been transformed and figuring out what transformations are taking place, we're going in the opposite direction. We're going to be given the transformations and we have to write a function. So we have to write a transformed function is what we're trying to do on these. We are using function notation. So remember, the original function would just be in this notation f of x. It could use different letters like we do here. We're using g of x, h of x, j of x, etc. Okay, so let's do these examples together. So number one says f of x is shifted 3 units left and 4 units up. So what we want to do here is we want to write the transformed function. So f of x is our original. And we want to write a transformed function that's shifted 3 units left. So when something is shifted to the left, I know it's going to be affecting the x-axis, so it's going to be on the inside. But also remember, when something is shifted, or when something is on the inside with the x, it would actually be the opposite operation. So shifting units to the left, we would be subtracting c, or sorry, opposite operation, we would be adding c on the inside of the x. Just that operation would look like this, f of x plus 3. So that would be shifting the original function 3 units left. But I'm not done yet. I also need to shift half 4 units up. So if something is shifting up or down, it's affecting the y values. So that's on the outside. And when something is affecting the y, it just does the operation we think it would do. So plus 4 would shift up 4. Or 4 would shift, we would have to add 4. So I would put up plus 4 on the outside. So this is what my transformed function would look like. F of x plus 3 plus 4. So we were writing our transform function here. We knew the transformation. We had to write the transformed function using the function notation. So f of x plus 3 plus 4 would be the function f of x, but shifted left 3 units and 4 units up. All right, let's look at number 2. Number 2 says g of x. So we're using a different name for our function. This is function g for our original function. G of x is shifted 4 units right. So if something is shifted to the left or the right, I know that is affecting the x-axis, so that's going to be on the inside. But remember, when something is with the x, it's going to be the opposite operation. So 4 units right is actually going to be a minus 4 with the x. Okay, so just that part of it, f of x minus 4 would be, whoops, not f of x. This one, we're supposed to use g of x. So g of x minus 4 would be the original function shifted to the right 4. But that's not all. There's another operation. This is also shifted units down. If something is shifted down, it's affecting the y values. So it's on the outside. And it would just be the operation that we see. So down would be minus 3. And that would be on the outside. So I would put the -3 on the outside of our function. So here's what our transformed function would look like. G, that's our original, g of x minus 4 minus 3. That would be g of x shifted to the right 4 and down 3. So that's all we're going to do here is write the transformed function using our function notation. All right, numbers 3 and 4, we got a couple more. So number 3, we have h of x as our original function. And this is shifted 2 units left, then reflected over the y-axis. So if something is shifted to the left or the right, if it's to the left, I know it's going to be affecting the x values or inputs. And remember, anything with the x is the opposite operation. So a 2 units to the left would actually be a +2 with the x. Okay, so that transformation, we're using function h as our original. Just this part of it would be h of x plus 2. But that's not the only transformation. There's also a reflection over the y-axis. So on a reflection, I know there's going to be a negative, or it's like multiplying by a -1. But I have to figure out whether that negative is on the inside or the outside. That's a little trickier on the reflections unless we have them memorized. If something is reflecting over the y-axis, that doesn't mean it's affecting the y values. Let's think about that before we say what's happening. So I'm going to kind of draw an illustration here. If something's flipping over the y-axis, here's the y-axis. If something's flipping over the y-axis, it's flipping left to right. So this is actually affecting the x values. So this is a reflection over the y-axis is going to affect the x values or be on the inside. So that means I have to have a negative on the inside. So here's what this is going to look like because we already have the x plus 2 on the inside. Both of these are on the inside. So I would have h. I have to do the negative. I do the x plus 2 first, and then I put the negative in front of that. So here's what it would look like. Negative x plus 2 in parentheses. So h of negative x plus 2. This would mean we do what's in the parentheses first. So we're shifting the graph left first, and then we are reflecting it over the y-axis, which is what that negative is doing there. So that's our transformed function there, h of negative x plus 2. All right, last one is number 4. This time we are transforming j of x. So j of x is our original. This one has 3 transformations, and we do need to do them in the order that they're listed. The graph is shifted, j of x is shifted 3 units to the right. So I know that's in the inside or affecting the x values. And I also know anything with the x is going to do the opposite operation. So shifting to the right would be subtracting 3. So after this first step, I would have j is the original function I'm using, j of x minus 3. Okay, that's just shifting to the right. Then I'm reflecting over the x-axis this time. Again, with a reflection, we know we see a negative. If I'm reflecting something over the x-axis, make sure you know what value it's affecting. If something's reflecting over the x-axis, it's flipping, the points are flipping up and down, which actually means it's affecting the y values or the outside. So this means there's going to be a negative on the outside. So after that step, we would have a negative on the outside. It would look like this, negative j of x minus 3. So I put the negative on the outside of the function, and we put it in the front because it's multiplying by a -1. So I wouldn't put like -1 or anything, just a negative in the front. I'm not done yet though, because I still have one last operation. Then the graph is shifted up 1. So up is going to be affecting the y value, so that will also be on the outside. And a shift is going to be just adding or subtracting. In this case, since it's affecting the y, shifting up will be adding 1. So I know I'm going to add a 1 on the outside. So here's what my final shift or my final transformed function looks like. Okay, we already did negative j of x minus 3. Now I'm just going to add 1 on the outside. And here's what our transformed function looks like. Negative j of x minus 3 plus 1. Okay, so the x minus 3 is the shift to the right. The negative in the front is a reflection, and then the plus 1 is shifting up 1. So before we continue in the actual note packet, I just want to remind you a little bit about function notation and what it means as far as input and output. So I'm just going to make up a random function for us to look at. Let's say we have the function f of x equals 2x plus 3. Remember the notation f of x tells us the name of the function, and the whatever's in the parentheses is the input. So this is telling us the input is x. This whole notation, f of x, represents the output. So this statement is saying output equals 2 times the input plus 3. And that allows us to find the output for any input we want. One way to keep track of that is with an input-output table like this. So the x's are the inputs and the f of x is the output. For the input, we can pick any x values we want. So, because we can pick anything, we can plug in anything. So for example, say I pick a 4. I'm just picking a random number for x. If I plug it in, I'm plugging it in. This is my input, so I'm plugging it in for x. It would look like this. F of 4 equals 2 times 4 plus 3. And then I would simplify. 2 times 4 is 11 plus 3, or sorry, 2 times 4 is 8 plus 3 is 11. So when the input is 4, the output is 11. And I can do that with any number. So say I want to pick a 0 to plug in. It would look like this. F of 0 equals 2 times 0 plus 3. So remember, anywhere there's an x, we can write it with open parentheses and then fill in that 0 or whatever that input is. So f of 0, 2 times 0 is 0, plus 3 is 3. So when the input is 0, the output is 3. Okay. And we can continue this with any numbers. I can also plug in negative numbers. So let's say I plug in a -5. My function would look like this. I'm taking my function here and writing blank parentheses where the x's are. And so then I plug in the -5. So I would have f of -5 equals 2 times -5 plus 3. 2 times -5 is -10 plus 3 would be -7. Okay, so we're going to be using this to find some coordinate points on our parent functions today, except instead of just picking random x values, we're going to pick some specific x values so that we can have a good idea of what our graph looks like. But I just wanted to remind you, if we know the inputs, how we get those outputs there. All right, so now let's go ahead and continue with these notes. So we're still in the 2D. We're on the second page, the front of the second page. It looks like this. So on the examples we've seen so far, we've just used random functions. However, in algebra, most of our transformations can be done on parent functions to get new functions. So that's what we're going to fill in here is all these parent functions. And all of these parent functions, we're going to have to know the coordinate points on them or be able to find the points as well as what the shape of the graph looks like. So for parent functions are the most basic of a type of function. The parent function is the most basic of a type of function. Meaning that it's the most basic function that hasn't been transformed at all. So it hasn't been shifted or stretched or anything. It's just the most basic function. And we use it to get a bunch of transformed functions. So a parent function is the most basic of a type of function. And so these are all different types of functions: linear, quadratic, cubic, absolute value, square root, cube root. There's a bunch of other types as well, but these are the ones we're going to focus on in this unit here. All right, so a linear function. We've talked about linear equations before. There's always just x to the first power. So a linear function is function f of x equals x. F of x equals x. What we're going to be doing on all of these, so you do need room for all of these. I'm going to make a table of values on this side, and then I also am going to need to draw the graph. Okay, so on this side here, I'm going to make input output table. So I'm making an input output table with x and f of x. Even though we can technically pick any x values we want, the x values we are going to use, we're going to make sure we include a negative, a positive, and 0. So anytime that we can, we're going to use these x values. So these in your table, -1, 0, and 1. Then we're going to plug those in to our function to find our output. Okay, I'm going to show the work down here, but you don't need to show where this is coming from. I just want to make sure, so you don't need to type this. I just want to make sure you know where this is coming from. So remember, any time evaluating a function, I can rewrite my function. And anywhere there's an x, I'm leaving a blank parentheses. And so then I'm going to fill these numbers in. If x is -1, if I plug in a -1 for the x, I would just get f of -1 equals -1. So if I plug in a -1, my output is -1. Okay, then I need to plug in a 0. So if I plug in a 0, f of 0 just equals 0. So f of 0 equals 0. Then I need to plug in a +1. F of 1 equals 1. So when I plug in a 1, my output is a 1. Okay, so these can be written in a table, but those are also coordinate points on our graph. So you can also write these as coordinate points. This first coordinate point would be -1, -1. This also has 0.00 and then 1, 1. Okay, so in addition to knowing the coordinate points on the graph, we also need to draw the graph. So I'm going to just make my own XY axis. So draw your own coordinate plane. That's my X and my Y axis. I'm just putting a couple dashes in each direction because I only have a couple points to graph. So draw in the coordinate plane. And now let's plot our points. So we said we have a coordinate point at -1, -1, 0, 0, and 1, 1. And knowing what type of function this is will help us draw this. This is a linear function, which means it is a line. Our graph is a line like that. Okay. So I'll give you a few seconds to draw that in. So we made a table of values to find our coordinate points, and then we graphed them, and a linear function makes a line. So all linear functions are just transformations of this. All right, the second type of function is quadratic. So the parent function for quadratic is f of x equals x squared. So we talked about quadratic equations, and we know that means when we have an x squared. So a quadratic function also has an x squared. So we have f of x equals x squared. Again, I'm going to make an input-output table. X and f of x, and I'm going to include -1, 0, and 1 in my x values. So even though technically we can pick anything we want, we are picking those x values so that we have a negative, a 0, and a positive. All right, so let's find our outputs. These are our inputs. We want to find our outputs. Here's our function here. F of x equals x squared. So if I am evaluating a function, we can write it like this, where we write the x as an open parentheses. So first I'm going to plug in a -1. If I plug in a -1, we'd have f of -1 equals -1 squared. -1 squared becomes +1. -1 times -1 is +1. So when our input is -1, our output is +1. Then I got to plug in a 0. So if I plug in a 0, f of 0 equals 0 squared. 0 squared is just 0. And if I plug in a 1, f of 1 equals 1 squared, which is 1. Okay, so these are our coordinate points for a quadratic function. I'm going to write those down at the bottom. So our coordinate points are -1, 1, 0, 0, and 1, 1. Now I'm going to draw my graph. So draw your X and Y axis. And I'm just going 2 in each direction here. So draw your coordinate plane. And now let's plot our points. Okay, so we have a point at -1, +1, 0, 0, and 1, 1. Now, again, we need to know what the basic shape of this is to draw it in. A quadratic function is going to be a parabola or U shape. So let's draw in our parabola or U-shaped graph there. All right, so that's a quadratic function. It has the points -1, 1, 0, 0, and 1, 0. And when we draw it in, it is a parabola shape. All right, next function is a cubic function. The parent function of a cubic function is f of x equals x cubed. X to the third power or x cubed. I know you would have seen those in Algebra 2 at some point, but just like we are doing on the other ones, we are going to make a table of values. Okay, so we're gonna make our input-output table, so x and f of x, and we're gonna pick the same x values, -1, 0, and 1, so the same inputs. So let's find our outputs here. So here's our function, f of x equals x cubed. So when I plug in my inputs, when I plug in a -1 for x, f of -1 equals -1 cubed. -1 cubed, this means -1 times -1 times -1, which is still -1. Then I got to plug in a 0. So f of 0 equals 0 cubed, which is still just 0. And then I have to plug in a 1. So f of 1 equals 1 cubed, which is 1. 1 times 1 times 1 is 1. So here's our coordinate points on our cubic function. I'm going to write those down. So -1, -1, 0, 0, and 1, 1. So you might notice that this actually has the same coordinate points as the linear function, but the graph is going to look a little different. So let's draw a coordinate plane. Okay, so I'm going to draw my coordinate plane. And I'm going to graph my coordinate points, -1, -1, 0, 0, and 1, 1. But this is not a line, it's not linear. A cubic function is going to be a curved function. The right side of the cubic function looks like the quadratic function. It's like a U shape. So this half is like an upward facing U on the right. The left half is like a downward facing U. So it's like we took that left side of the quadratic and flipped it down. Okay, so this is like a squiggle function for the x cubed. The right end is facing up, it's an upward facing U, and the left end is facing down for a downward facing U. Okay, so that's what a cubic function looks like. F of x equals x cubed. All right, we got a few more we gotta draw in. I'll give you a second to make sure you got the cubic graph down. At the end, I'll put all of these back up so you can, if you missed anything, you can write down anything that you missed. All right, next, absolute value. The absolute value function is f of x equals absolute value of x. F of x equals absolute value of x. All right, we're going to do the same thing. Take an x and y table or an input-output table. So x and f of x. And I'm using the same inputs, -1, 0, and 1. And for my output, I'm going to plug them in to this absolute value function. So f of x equals absolute value of x. So if I plug in a -1, it looks like this. F of -1 equals absolute value of -1. Absolute value of -1 simplifies to just +1. Okay, now let me plug in a 0. So if I plug in a 0, f of 0 equals absolute value of 0, which is 0. And if I plug in a 1, f of 1 equals absolute value of 1, which is 1. Okay, so these are our coordinate points on our absolute value function. -1, 1, 0, 0, and 1, 1. So you might notice the absolute value function has the same points as the quadratic function, but it's going to be a different shape. All right, so let's draw this in. Draw in your X and Y axis. And draw in a couple tick marks in each direction. Let's plot our points. So we have a point at -1, 1, 0, 0, and 1, 1. This one, even though it has the same points as the quadratic, it is not a U shape. A quadratic function is going to be a V shape graph. So the two sides are straight lines. Okay, so quadratic function is V shape. Or sorry, absolute value is V shape. So it has the same points as the quadratic, but different shape. All right, we got a couple more to draw in. Next is a square root. The square root function is f of x equals square root of x. F of x equals square root of x. So first, like we've been doing, let's make a x and y or input-output table, x and f of x. Okay, before we fill in this table, this is the only one that we don't use these same x values. And I'm going to show you why. You don't write this down yet, because I'm going to show you why we can't use -1, 0, and 1. Okay. So on this function, f of x equals square root of x. If I try to plug in a -1, look what happens. F of -1 equals square root of -1. Square root of -1 is not real. It's an imaginary. So I can't plug in the -1. So this is the one case where I'm not going to use -1, 0, and 1. I am still going to use 0 and 1. But let's get one more number in our chart as well. I could use, for example, a 2, but I'm going to show you why I'm not going to choose a 2. Say I chose a 2, it would look like this. F of 2 equals square root of 2. Square root of 2 is a real number. It's just not a whole number. It's like approximately 1.7 something. It's irrational. So even though I could plug in a 2, I don't want to because I want to make it easy to graph. So the number I'm going to put in my table is actually a 4, because if I plug it in, square root of 4 will give me a whole number. Okay, so back to our table here. So now I want you to write that down. In our table, we're going to use 0, 1, and 4. So this is the only one where we don't use -1, 0, and 1. Instead, I'm using 0, 1, and 4. All right, so let's plug those in and find our outputs. So f of 0 equals square root, or f of x equals square root of x. If I plug in a 0, f of 0 equals square root of 0, which is just 0. So when the input is 0, the output is 0. If I plug in a 1, f of 1 equals square root of 1, which is 1. So I have a 0.11. And if I plug in a 4, f of 4 equals square root of 4, which is 2. That's why I chose 4 as an input, so I'd have a whole number output. Okay, so those are my coordinate points for the square root function. 0, 0, 1, 1, and 4, 2. All right, let's graph that. So draw your coordinate plane. Draw your X and Y axis. This one, I am going to have to go a little bit farther on my X axis. All right. So drawing your coordinate plane, and then let's plot our points. So I have a coordinate point of 0, 0, 1, 1, and then 4, 2. So this graph points out to the side like a half rainbow, like a rainbow here, but it just keeps going to the side. So it's kind of like if we took the U-shaped graph and turned it sideways, but only using the top part of the U here. Okay, so we're using, it's like a sideways U, but only half of it. All right, so that's what the square root function looks like. And like we said, that's the only one where we use different X values. Last function, last parent function we need to know is a cube root. So the function is f of x equals cube root of x. F of x equals cube root of x. All right, like we've been doing on all of these, we're going to make an input-output table. This one I am going to choose the same ones I did on all the other ones, -1, 0, and 1. So in my input-output table, I'm choosing -1, 0, and 1 as my inputs. And so when I plug them in here, looks like this, f of x equals cube root of x. When I plug in a -1, so -1 is my first input, f of -1 equals cube root of -1. We can do a cube root of a negative. Cube root of -1 is just -1. Because -1 cubed is -1. Okay, so this one we can do a negative because it's a cube root. Okay, so cube root of -1 is -1. Then I plug in a 0. So cube f of 0 equals cube root of 0. Cube root of 0 is just 0. So I have a 0.00, and then I need to plug in a 1. F of 1 equals cube root of 1, which is 1. So cube root function has the points -1, -1, 0, 0, and 1, 1. Again, you might notice this has the same points as the cubic function and the linear function, but this one is going to look different as well. All right, so let's draw what this one looks like. So drawing your X and Y axis. And then let's plot our points. So our points are at -1, -1, 0, 0, and 1, 1. Okay. This is not a line. It is going to be a curved function, but it's curved in a different way than the cubic. It actually looks more like the square root. So the right side of the cube root looks just like the square root. It curves out to the side like this. It's like that U shape that's sideways, but only the top half. The second part of the graph is still going to be like that sideways U, but facing the other way. But that's going to use the bottom half. So this one's like a sideways U going out to the left. Okay, so there's what the cube root function looks like. So the cubic function points up and down. This one points to the right and to the left, like that. Okay, so those are our functions. I'm going to put the whole thing up in just a sec so you can see. Okay. So, oops, hold on. Make sure you have everything filled in here. So we've got our coordinate points and the graphs. So those are the things that we need to know or be able to find on all of these parent functions. One thing you might notice about every single one of these functions, they actually have 2 points in common. The 0, 0 and the 1, 1, they all have in common. It's just that third point. So when the x is -1, we have to actually figure out that output. Okay, so take a screenshot of that if you need to, or copy down anything that you don't have yet, because we're going to need to know all of these functions. So again, there's going to be things in here that you might need to actually study and memorize, because we'll use these parent functions to do transformations.